I'm Dr. Rebecca Clem, and I'm going to show you a fun activity you get to do. All you need is paper, tape, and scissors. It's called turning two circles into a selfie square frame. And it's a good reference to the history of mathematics where people wanted to figure out if they could find a square and a circle with the same area. And once we realized pi was hiding in circles, we realized it couldn't be done. But this is my reference to that, turning two circles into a square. We're going to start with strips of paper, just plain old strips of white paper here. And on each one of them, you turn them into a circle. Actually, in high-level math, it's called a ring. Looks like a donut. So you must tape it well. Okay. All right, so I made one ring. I make another ring. Now the transformation, this is transformational geometry. The transformation happens when you put the two rings together perpendicular, just like you see in the streets when they come together. And so we put them together and must tape them very well, because what I want you to do in the transformation is you actually are going to cut down the middle of each of these two circles, or rings, as people call them in topology. It's called topology. Is the high-level geometry lesson. Very important part of the future of mathematics. So now we're going to take each one of these circles or rings and cut down the middle. Start anywhere you like, and you cut all the way through. Okay, until they meet. Now, does that look like a square? No. Does it look like a selfie frame? No. You can decide what you think it is. You can wear it as headphones. You can wear it as handcuffs. You can do all kinds of things. But remember, the idea was to do the same to both circles. So if you think about what happened, the one circle has been now cut. So we need to do the same thing for the other circle. And if we open it up, it makes it very easy to do. And we go right down the middle, all the way, clip, and you have your selfie square frame to take your picture. Now, let's don't stop there. Let's do some scientific method. Let's suppose you have one strip a different color. For example, hot pink, and the other one white. Where do you think, what's the hypothesis of where the pink is going to show up and where will the white show up? You can think about it yourself while I actually do this. I would say there are probably two choices, either opposite. You could have it be the opposite part, which would be the top and the bottom, or you could have it be around the corner, one here and one here. Let's see. This is a hypothesis, and now we can actually get the data and see whether we agree with the hypothesis of which you decided. So here again, we're going to put them together perpendicular, tape them. Perpendicular again, remember. Now we cut down both sides, down the middle, excuse me, of each one. Here goes the white one, and it should come right around to where you started. Okay. Now we cut the other one. You may have a hint of where it's going to end up now. We're cutting down the pink, and what do we have? The pink is on one side and the white is on the other. You can think about, how does that happen? Why does it happen that way? Now the next thing we can do is say, what if I don't do it as quite a square? What if I change the angle? All right, let's try that. One circle. Now let's keep the pink. Let's make another circle. But don't make it exactly perpendicular. Let's change the angle. What do you think the shape is going to look like when you get done? Will it be a square? Will it be something else? What might it be? Okay. All right, let's cut. I have been doing this for many, many years. Most people only see it at graduate students because this is high-level topology. It's the same idea of transformations. Some of you who like to make clothing, you could talk about transformational math from fabric into clothing. Look what we got, a parallelogram. The angle, and I would like you to think, if you do this, what are the angle sizes here compared to the angle that you actually made when you constructed the two circles together? How did the angles match up? Okay. Now, one other thing let's do. Let's make the two circles not the same size. What might happen now? While I'm doing that, I want you to think fundamentally a question, because you know pi is inherent in every circle. What happened to pi when we turned it into a square? Where did pi go? He's got to be hiding there somewhere. Where is he hiding? Oh, so that's a question I want you to think about, and maybe you can actually talk about with your teacher or ask me later. Where did pi go when you turned it into a square? All right. Here we now have, oh, I didn't quite do a very good job. I'm going to turn this into a shorter one. Let's make one of the circles very small compared to the other one. That's what I wanted to show you. So I'm going to make one of the circles smaller, but it's still going to be perpendicular. What do you think I should get out as a shape when one of them is smaller than the other one? I'll let you think about it, make your hypothesis. Now I will cut down through and see what happens. Cutting through the larger one. There's the two rings. And we cut through the other one, and what do we have? It's not that much different, but it's more a rectangle. It's not a square anymore. And where does it come as a rectangle? Because the two circles were different sizes. And you can compare the length of the two sides of the rectangle to what the original sizes of the two circles were. Okay? Now to get even more fancy, we are going to add what's called a Medius Grip. And you can look up Mr. Moebius, the mathematician, M-O-E-B-I-U-S, and he came up with this change transformation of a piece of paper, two sides, give it a little twist, and you tape it together with one twist. Magicians have used this for a long time. It isn't magic though, it's really topology, transformational geometry. So now when you have this piece, if you were a little mouse going around on a racetrack, you will find out that it has only one side. That blows your mind a little bit. It's a one-dimensional shape now that came from a two-dimensional shape. Let's cut down this one and see what happens now with one of these shapes. So we're going to go down the middle of the Medius strip. And what are we going to find? A bigger one with a double twist. Okay. I'm going to leave you with one more and then a couple questions for you to think about. Let's do a Medius strip where I don't go down the middle. I'm going to do it fractionally. So again, you take one twist to turn it into a Medius strip. Now you know it's an... And artists have made furniture out of this shape. They've made scarves out of this shape. You could be very constructive and very inventive to use these unusual transformational shapes in all kinds of walks of life. So now let's not go in the middle. Let's take it 1/3. Okay? So if you go down 1/3 of the distance from one side to the other and make a cut. Okay? So around I go. And I come to where it would have been a connection, but it isn't because I'm now on 1/3 and there's the 1/3. So I'm going down the middle of the remaining 2/3. So, you know, half of 2/3 is down the middle. Okay. Now, here we go. I'm connecting back to where I started. And what do I have? Two interlocking. One is a Moebius here with one loop, and here's one with a double loop. If you do these have direction, sometimes you can figure out how to turn these into looking like a heart shape, and you can get a reverse heart shape. You can play a lot with Mobius strips and do fun things. Now, what you can do and work on your own would be to say, let's see what happens if we use a Mobius strip instead of a regular circle. So let's go make a Mobius strip and maybe make one regular strip. But you can then think about what happens if you use two Mobius strips. So let's make one Mobius strip of pink. And one Mobius strip of white. And let's put them together like we did with the circles. Okay? I'll put them together sort of perpendicular. Look, they look kind of fun, don't they? What is going to happen? And you can think of your ideas and try them out, and I will leave more ideas for you to figure out totally on your own. So let's cut down. Should I go the middle? Lots of choices here. You could go down the middle, you could go down the thirds, you could do one of each. You could do one Mobius strip and one regular circle. You can do all sorts of activities of your own after this little example session here. And you can send me your pictures. What happened? What was your idea? What did you think would happen? And were you surprised, or was it just what you had anticipated in your hypothesis? Now I've cut down one, I need to cut down the other. What's going to happen? What did we get? Two pieces. Right? Very different, and yet each one of them has now a top and a bottom. It's not a Mobius strip. This one has a bit of a twist, and the other one did not. Mobius strips are fascinating. Moebius is the Swiss mathematician, I believe, who came up with the idea. Mix them, try your circles, put them together, measure, create, and have a great time learning in transformational geometry. This is the Numbers Lady. I'll pass it back to Dr. Wesselman, and we'll talk about it. You can send your pictures, and we can talk more later about what you found out and what this is about. Thank you.